Greetings! Welcome to the fourth lecture of ECE 113, and in this lecture we'll be talking about mixers, how to operate, how does a mixer work, how do we design the mixers. Basically, the operation of mixers is just to multiply two signals. That's it. These are nonlinear devices, and the output is the product of two inputs. The inputs generally have different frequencies, assuming sinusoidal. If these inputs are sinusoidal, then the output signal contains, and this is important, the sum and difference of input frequencies. If S1 of t is the message, S2 of t is the local oscillator, then we have a mixer for communication systems. So if we have a message with frequency omega 1, it's sinusoidal. Your carrier is omega 2, then the output of the mixer is this. And if we use a trigonometric function or trigonometric identity, we get this signal right here has a sum frequency and a difference frequency. So the output has two individual frequency components, your sum and difference of the individual frequencies. If S of t is an arbitrary signal with a spectrum S of f, and S of 2 is some carrier with a frequency f sub LO, your output is equal to this. And if you take the Fourier transform of that, we have this and this. We have two components in the Fourier transform. So one is added to one is added with FLO and the other is subtracted. Okay, so the mixers are essential in shifting the frequency content of a signal. As we can see in this operation in the screen, it leads to up conversion for easier antenna design. That's why we do this. Or down conversion for easier signal processing. So recall that if we move higher in frequency, it gets harder to design filters to process the signal. However, if we use lower frequencies, the antennas that we're going to use are actually very large. That's why we have mixers in between some IF, intermediate frequency, and some RF, radio frequency. So let's differentiate them first. A baseband signal is a signal with a narrow bandwidth centered at f is equal to 0. Not to be confused with IF, which is the frequency band used for signal processing. But sometimes these bands coincide with each other. So take note of that. If we have S1 of t, a baseband signal, the spectrum will look like this. After mixing, the spectrum becomes this. Okay? So some notes, not all signals are baseband signals. All signals are real. Of course, there's no such thing as a complex signal in the real world. That means the signal has positive and negative frequency components. And this is the case for signals in immediate frequency. So the positive frequency component has a certain symmetry with the negative frequency component right here. Okay? So an example would be your speech signal. It exists in 200 Hz to 40 Hz. If S1 of t is a speech signal, so let's decompose this speech signal into its positive frequency component. Wait, I'm sorry. Okay, so let's differentiate this signal in its positive frequency component and its negative frequency component. Right? And we have right here, since this signal exhibits Hermitian symmetry, then it follows that this S1 negative, right here, the negative frequency components is your positive frequency component reflected. Okay? In essence, it's this one. So this is just an example. Let's say it's a speech signal from 4 kilohertz, sorry, from 200 hertz to 4 kilohertz. Okay? So if we try to upconvert that using the modulation property of Fourier transform, this output will become this equation right here, and S naught of f is this equation. Since knowing that S1 of f is your positive plus your negative frequency component, we get two terms right here, your useful signal and some image signal. To visualize that, we have this. Right? The original spectrum is something like this at the middle. If we upconvert them, we have this and this. Okay. Actually, as you can see, the useful information comes from what resembles your original signal, which is this and this. But what happens if we upconvert them? We actually have some form of images. And when we transmit these images, not only do they consume bandwidth, they also consume power. That's why we must delete these images before we transmit them. Unless, of course, you're using double sideband for your AM signal. So, one way to delete the images is to use a bandpass filter to select depending on what band you want. So, these images are actually interchangeable. It could be this is your useful information, and it follows that the other one is your image. We'll call this the upper sideband, and the other one lower sideband. To delete the image, it depends on what you need. Basically, you just select the signal that you want. Is it your upper sideband or is it your lower sideband? And this filter is called the image rejection filter. Now, once you have transmitted that and you have received it on another end, how do you downconvert this spectrum? So the Fourier transform becomes this. Let's say we use the upper sideband. If we mix it with another local oscillator for your receiver, we have two signals right here. One is your original signal, the other is some high frequency component. Right? And it's scaled by 1/4. So this is your upconverted message. What happens is you have some message estimate and your images. And you want to filter out your original signal. Okay? And to delete these images, you just use a low-pass filter. However, in some practical systems, the receiver antenna actually picks up the transmitted signal and some signals outside the frequency of transmission. Basically, the antenna can also, pick up some signal right here that is near your desired signal. And it gives rise to what we call the image problem. Right? So let's look at that spectrum that you saw earlier. So we have your upconverted signal right here, your noise signal or an interference that is near your signal. Let's say it's just a sinusoid, so we use delta functions to represent that. The input spectrum to the mixer is just a sum of your desired signal and this interfering signal. If we get the output after down conversion, get this equation and this equation. Just rearranging some terms, we have the baseband terms or the low frequency terms and the terms that will be filtered out after filtering out after low pass filtering. Okay. The resulting down converted spectrum looks like this. Your message is corrupted by the image frequency right here. How do you solve it? Well, you can just filter it out before the mixer. So, assuming that your upconverted spectrum is centered at 1 GHz and your bandwidth is 1 MHz. To filter that out, your Q factor must be 10 to the 3. So we'll discuss more on this later, but right now, just accept that a large Q factor is impractical. How do we deal with this image problem? The solution is using a selective receiver. Instead of directly down converting, like what we did in this problem right here, from here we down converted it, becomes this. Instead of down converting, well, we can just down convert to some IF at which the signals won't overlap with each other and filter out the noise and then demodulate it or down convert it further. This is actually your superheterodyne receiver. It improves your receiver selectivity and rejects the image frequencies. Okay. We now look at an important parameter for your mixer or your receiver in general, and that is your image frequency rejection ratio. Basically, after demodulating it, filtering everything out, the image frequency rejection ratio is equal to the power of the desired divided by the power of the image. Another solution is the use of your phase discriminator. But this design is more complicated and more costly than your superheterodyne architecture. Okay? However, it provides a very large image rejection ratio. Because ideally, your image will be completely cancelled at the adder. Right. Practically though, mixers are nonlinear devices. Okay? Since we're trying to multiply signals, we're doing a nonlinear operation. And that would mean that most nonlinear devices can be used as a mixer. Recall that the input-output relationship of a general nonlinear device is this equation right here. So what if we add the signals first and apply them in a nonlinear device? So we have done this before. So we get this equation and we simplify that expression. Okay, we have some terms that are multiplied with each other. Right? So if we look at the IMD spectrum before, right? So it is assumed when we're solving the IMD, omega 1 and omega 2 are close to each other. Therefore, their difference is less than what they are. This is your down conversion process. And as you can see, these are your desired signals. You can actually filter all of this out right here and just get this signal, which is the down converted signal. If omega 1 and omega 2 are very far apart, we get an up conversion process. Right? So from a low frequency, we get an up converted signal right here. And the desired outputs is this and this. Okay? However, it's near or between them is a spurious output, omega 2. This omega 2 can actually be removed by finding a correct bias point to avoid that. So the devices capable of mixing would be your diode, BJT, and MOSFET, basically your nonlinear devices. And there are mixers whose design are diode-based and some transistor-based. Let's look at the diode-based design first. First, look at this circuit. You have two sources that are added together, and then uh, the voltages are input to some diode. If we invoke Taylor series, the current output becomes this expression right here. And let's just consider it until the second harmonic only. Let's just write this right here. So if we do that, we get this equation. And we get the current output with the multiplied term. Right? To convert that to voltage, you just need to pass it to a filter. This is a single-ended diode mixer. Okay? This diplexer right here adds C of t and X of t. Right? So this diplexer actually isolates C of t and X of t, so they won't interfere with each other. These three components separate the DC and RF components. Okay? So a capacitor is open to DC, but is short to very high frequencies. An inductor is short in DC, so it will bias your diode, but is open in RF. And finally, your low-pass filter will filter out high-frequency components. You get your message signal. So this is actually a down converter circuit. Alright. So for a diode-based design, it needs some way to isolate your local oscillator and your RF and IF components. So if you have high-frequency circuits, we actually use diplexers. High-Q filters can also be used for low-frequency circuits. Okay. So the bias point for the diode is needed, and basically you just need to find the right bias point so that you have your desired output. Right. So some important points: you separate the three signals from each other. This signal must be separated from this signal so that they won't interfere with each other, and also you need to separate the voltage by using chokes and large capacitances. Okay. For a transistor-based design, let's look at this hybrid pi model of any transistor. We find a bias point by varying your transconductance. So it is chosen depending on what you have. For amplifiers, your transconductance region is chosen to the point where it's approximately constant. But for a mixer, you want that bias point, the bias point to have a GM that has a large swing. Okay? Since your output is equal to GM times your input and some RO, which is your output resistance, you choose the bias point at which GM behaves or changes very fast compared to your input. Okay? And we use one of the signals, mainly the local oscillation, to be the input that biases this GM. Because of using LO as a bias, what happens is that the GM changes rapidly, and it results into a GM with this equation right here. Okay? And the effective small signal model becomes this. Your output voltage is equal to GM times R0 times VI. Okay? Something of the sort. And we get a term that is multiplied. Okay? So an example circuit would be this Again, a diplexer is used to separate LO and RF. Some chokes are used for biasing, and then a filter is used to remove the high frequency components. Okay. Mainly, a FET is used because it's a square law device. So what is a square law device? It means that the output is the square of the input. So this IF is equal to the sum of these two squared, which creates your multiplying effect. Okay. Some important parameters for mixers would be the frequency range of its inputs and outputs, the maximum powers, your loss, the noise figure, and of course, your 1 dB compression point and IIP3. The conversion loss is the power loss due to using the mixer. Okay, so it's basically just your output power divided by your, sorry, if it's a down converter rather, for a down converter, the conversion loss is the available output power, input power for RF divided by your IF output power. And this parameter is strongly affected by the LO signal power. So lower power could mean that it cannot switch between the operating modes of transistors and diodes. The noise figure, your diode-based mixers generally have lower noise figure than transistor-based mixers. And it also depends on what type of signal you're using or you're transmitting. The noise figure for SSB is actually twice the noise figure of your DSB. Because if you use SSB, you're just transmitting half the power of your DSB. Okay? So the linearity and port isolation, here are some notes. The IP3 of your mixer ranges from 15 to 30 dBm. And your isolation, basically you just need your RF and IF ports to be decoupled with each other. They must not interfere. Okay. And just basically some notes. We won't characterize them from in this lecture. You just need to know how to design them. Okay. So just some types of mixers. We've discussed this. Others you can find in the book. Okay. And this is some comparison between them. So just refer to the uploaded slides on what to use for your design project if you will be designing mixers. So that's the end of this lecture. Thank you for listening. I'll see you next meeting. Oh, yeah, I forgot. If you have any questions or comments, do not hesitate to leave a comment in the comment section below. Thank you for listening. See you next meeting.